Next talk is Adaptively Secure Attribute-Based Encryption from Witness Encryption by Brent and Daniel will give the talk.
Right, thank you. So this is Adaptively Secure Attribute-Based Encryption from Witness Encryption, and this is joint work with Brent Waters. So let's start with what attribute-based encryption, or ABE, is. It's a special type of encryption that gives us fine-grained control over which keys can decrypt which ciphertext. There's some master authority that knows the master secret key, publishes a master public key, and for any user that comes in, it can generate a special secret key for that user that's tied to policy F, which determines which ciphertext that user can decrypt. When we create a ciphertext for some message M, this ciphertext is tied to an attribute X, and a user with a secret key for policy F can decrypt a ciphertext with attribute X if f of X is equal to 1. When it comes to security, we consider an adversary that gets the master public key and many secret keys for different policies Fi, as well as a ciphertext with attribute X. And the goal is that if none of these, if Fi of X is equal to 0 for all of these policies Fi, meaning that the secret keys are not qualified to decrypt the ciphertext, then the adversary should not learn anything about the encrypted message. So the question is, where do these policies Fi and the attribute X come from? How are they chosen? And so they're going to be chosen adversarially. Ideally, we'd like to do this with fully adaptive security. So the adversary can choose the policies Fi and the attribute X fully adaptively, meaning it can see the master public key, get a bunch of secret keys for different policies Fi, then adaptively choose the attribute X, get the ciphertext for X, and then choose additional policies Fi and get secret keys for them. That's the ideal. This turns out to be often very difficult to achieve, and so people have also considered a relaxed notion called selective security, where the adversary has to choose the attribute X at the very beginning of time before even seeing the master public key. Okay, so what's known about ABE? So the initial construction of ABE was for policies that could be expressed by NC1 circuits, and we had this from bilinear maps. Later, under the learning with errors assumption, or LWE, we got ABE where the policies could be arbitrary circuits. And lastly, we also know the latter from a generic primitive called witness encryption, albeit a pretty heavy hammer. Okay, but all of these initial schemes, unfortunately, were only selectively secure. And when it comes to adaptive security, much less was known. So in particular, we do have a construction of adaptively secure ABE from bilinear maps for NC1 circuits. This is using something called the dual systems methodology. But when it comes to LWE or witness encryption, we did not know how to get adaptive security. We could only do it using an even heavier hammer called indistinguishable obfuscation, or IO. And so the main result of this work is to show how to get adaptive ABE for all circuits from just witness encryption rather than IO. Okay, so in particular, the result is adaptive ABE for circuits from witness encryption, plus additional assumptions that are fairly standard. So in particular, statistically sound NISICs, which we know how to get for most standard assumptions like factoring or LWE or sub-exponential DDH, plus one-way functions. So you might ask, why do we care about getting adaptive ABE from witness encryption? We already had it from IO. Both witness encryption and IO are kind of heavy hammers. Why do we care about one versus the other? And the main reason is that witness encryption seems to be much less of a heavy hammer than IO. And in particular, there's two consequences. One is we have more candidate constructions of witness encryption than IO. For example, we know how to construct witness encryption from some variant of something called evasive LWE. We don't know how to get IO from that. And there's kind of more hope of getting witness encryption maybe than IO. It seems to be an easier primitive. But I think the last bullet is really the main point here. Because witness encryption seems to be less powerful than IO, by kind of tying one hand behind our back, it forces us to do more work, come up with new ideas, and hopefully these new ideas or techniques may be independently useful for getting adaptive security from other assumptions as well. Okay, so that's a good segue to actually start talking about the techniques. So the main tool, the main kind of technical way that we achieve this is by introducing a new primitive called the functional tag system. This is something that we are able to construct from just one-way functions, and then we use it with witness encryption to get adaptive security. So let me tell you what this primitive is. A functional tag system lets us create tags for functions f, and also so function tags for functions f, and input tags for inputs x. And we can create these types of tags in one of two different ways. The first one I'll call dummy is just by some public randomized procedures that are completely independent of each other. So there's nothing tying tag f and tag x together. And then there's a smart way to generate this using a shared key, secret key k. Okay, so two different ways to generate these tags. And in addition, there's a public test that tests whether a combination of a function tag and an input tag causes some trigger event to happen. And we want two properties. So if you create dummy tags with any function f and any input x, the probability of them triggering should be negligible. They will almost never trigger. On the other hand, if you generate smart tags for function f and an input x with a common key k, then they should always trigger if f of x is equal to 1. And lastly, the security property says that a fully adaptive adversary that sees one input tag and many function tags cannot tell whether everything is dummy or everything is smart with a shared common key, as long as all of the outputs of the functions are 0. In other words, in the case where nothing ever triggers, you can't tell if things are smart or dummy. So security only holds in the case where there's no functionality, nothing ever triggers. Okay, so I'll tell you how to construct this in from one-way functions in a little bit. But first, let me show you how to use functional tag system to build adaptive ABE from witness encryption. And essentially, it's an adaptation of the previous construction of selective ABE from witness encryption. We're just going to incorporate these, this kind of functional tag system inside to get adaptive security. So the master public key and the master secret key are just the verification key and signing key of some sort of a specialized signature scheme called a constraint signature. I'll tell you a little bit more about what we need from there in a little bit, but it's something we can construct from NISX. And a secret key for function f is just going to consist of the function f itself, a dummy tag for the function f, and a signature for the pair f comma tag of f, using this constraint signature scheme. And to create an encryption of some message m with respect to an attribute x, we're just going to give out the attribute x, a dummy tag for x, and a witness encryption of the message with respect to a statement that says that there exists some function f along with a tag of f and a signature pi, such that pi is a good signature of this pair f comma tag of f of x is equal to 1, and the tags don't trigger. Now, witness encryption ensures that if this statement is true and you have a good witness, you can decrypt. So in particular, if you have the secret key for f, you can decrypt correctly. But if the statement is false, then the message is hidden. And the security proof works as follows. So the very first step of the proof is let's switch all the dummy tags for smart tags. And by the tag system security, this cannot be distinguished because nothing ever triggers. Like none of all of these fi of x is equal to 0 for the tags the adversary sees. Then once we do that, we're going to constrain the signature scheme so that valid signatures only exist for pairs f comma tag of f that were generated in the smart method using the correct secret key. And the property we need of the signature scheme is that as long as you only get signatures for such values, you cannot tell the difference. And that's what's happening in this game. So you cannot distinguish this. And once we do that, now the statement in the witness encryption is just always false, because whenever f of x is equal to 1, if the tags are smart, then the trigger event does happen. And now, so once the statement is false, you can use the secure witness encryption to ensure the message is hidden. So that's the entire proof. So now let me tell you a little bit about how to construct this functional tag system in the last few minutes. So we're going to use garbled circuits. Essentially can just rely on the standard Yao garbled circuit construction. But we're going to rely on a special property of garbled circuits that was also used previously called blind garbled circuits. And this property says that if you see garbled circuit of a circuit C and a garbled input X, then the two values, the garbled circuit and the garbled input, look uniformly random as long as C of X is a random value. Okay, so they just look like uniformly random bits. Okay, so using garbled circuits, we're going to think of the function tag as a garbled circuit we're going to think of the input tag as a garbled input, and we're going to define the trigger event to happen if the evaluation of the garbled circuit on the garbled input outputs some special value, let's say 1 to the n ones. Now, the smart tags will be real garbled inputs and garbled circuits, where the circuit outputs 1 to the n if f of x is equal to 1, and otherwise just outputs some random value. And the dummy tags are just going to be uniformly random bits. And so essentially, the blind garbled circuit security ensures that if you only see garbled circuits and garbled inputs for values where f of x is equal to 0, so these circuit output randomness, they just look like random values altogether. Except there's an issue. Garbled circuits only provide semi-adaptive security when the input x is chosen before the circuit. Here we want fully adaptive security. And it turns out we can fix this issue using techniques from adaptively secure garbled circuits that show how to get adaptive security for garbled circuits in certain special cases. And it turns out we can make this fit into those special cases. This is a little bit tricky to do, so see the paper for all details. I won't have time to explain all of it, but that's essentially it. And so I want to just leave you with 2 open problems. The first one is, can we make the scheme succinct, meaning that the encryption time and ciphertext size is smaller than the circuit size of the policies we can handle? So this is something we know how to do from LWE and IO, but we don't know how to do it from witness encryption. This is even open in the case of just selective security. And the second open question is, can these techniques be used beyond just AB from witness encryption? Can we somehow use this functional tag system or some of these techniques to get adaptive security more generally or for more assumptions? Thank you.
So if I understand correctly, the key, like the smart tags, are only used in the proof, are not used by any real users. And how do we select the key then in the proof? Is it just purely at random?
That's correct, yeah. So in real life, there's no key for these. You're only using dummy tags. They're non-key. They're just random values. In the proof, you pick some random key for the system and use it to generate all the tags. So the smart tags in the key in the secret keys, as well as the tag in the challenge ciphertext.
Thanks.